Welcome everyone to your final topic in Calc BC. We'll do this today, probably put something together on Thursday to reinforce this a little bit, but then we've learned everything that we need to learn this year. Probably put together a quote-unquote test for next Tuesday or Thursday, one or the other. I'll let you know for sure on Thursday. Then those who need a test grade to improve their grade, you'll have that opportunity next week, one way or the other, Tuesday or Thursday. You'll see at the top here what we're getting into. It's called Taylor series, Maclaurin series. First, I want to review what we did last week, because a Taylor series and a Maclaurin series they are power series. Power series is what we talked about last Thursday, which now, since we only meet 2 days a week, has been a while. So I just want to do a quick little review of what we did last week. So I'm telling you to, let me get this in black, use the series represented by the function 1 over 1 plus x to approximate a natural log of 2. So if you remember, one of the things we did last week when we did the power series is we talked about, again, the sum of a geometric series. That's this formula here, where we have our first term in the numerator, and then it's always 1 minus your common ratio. If you look at what we have to work with here, what that would tell us is our first term was 1, and instead of 1 minus your common ratio, since we have a plus x, what that would have to mean is our ratio was a negative x. So if I wanted you to use this series represented by a function to approximate the natural log of 2, first thing I'm going to do is to write the series for this. Since we're going to be multiplying by a negative x every time, since we want our first term to be a 1, I'm going to do that by saying n is a 0. I'm going to do a negative 1 to the n and then x to the n. So that's really just the same as a negative x raised to the nth power, but it's nice to pull this out. It's a little easier to see what's going on when that happens. But when you do that, think about our series. If n is a 0, you would get negative 1 to the 0, which is 1. X to the 0 is going to be a 1. That would give us a first term of 1, which is what this is telling us we were supposed to have. Common ratio is now a negative x, so you're just going to start multiplying by a negative x every time. That's going to change our signs, so on and so forth. That's the polynomial term that we would get. This is going to be our series. So then the question is, approximate the natural log of 2. Well, what this is an approximation for this function, 1 over 1 plus x. We graphed something like this the other day, and the more and more of these terms that we were to use to graph, the more and more that graph starts to look just like the original function, at least within the area that we're converging. How can we get a natural log out of this? So here's what this gets into. We'll deal with this a little bit today as well in the new notes. There really is no natural log in these, so if I want to create a natural log of 2, think about what you could do with this function here to create a natural log. If I were to do the antiderivative of this, since this has an exponent of 1 and our coefficient of 1, the antiderivative of the right-hand side would be equivalent to the natural log of 1 plus x. Well, since this polynomial slash series is equivalent to this function, the series in particular, then if these are equivalent on each side, then it's basic algebra. Whatever I do to one side, I've got to do to the other. So if on this side I did the antiderivative, which we said we did, then that should allow me to do the antiderivative of the polynomial, even the antiderivative of this function. Now, the function part is something that you're not really going to be tested on, but we really could just do the antiderivative of this and get an x to the n plus a 1. That would be our new series. So this series actually would represent this function. What we're going to do is do it term by term to do our polynomial and create an approximation. So the antiderivative of 1 would be x. The antiderivative of x would be x squared over 2. The antiderivative of x squared, x cubed over 3. And we would continue on for however many terms I were to ask you to do. And you'll see today how you'll know what to do. So the natural log of 1 plus x we can approximate with these terms. And the more of these terms we include, the more accurately we're going to get the value of a natural log of 2. So first, let's talk about what the natural log of 2 is. It's like 0.693. If we were to throw that into our calculator, 0.693. Well, if I want to use the polynomial term, the way I can do that is by plugging in for x. Since I want the natural log of 2, I would want my x to be a 1. And again, basic algebra tells us if I do this to the right-hand side, I'm going to have to do the same thing to the left-hand side. So now, wherever I have an x, I'm going to be plugging in a 1. So instead of x minus x squared over 2 plus x cubed over 3, and then however many terms we would use. What did I do wrong here? This should be a 4, sorry. X to the 4th, this, over 4. What we were supposed to do is let all of our x's become a 1. So think about what now our values are going to be. If we know that the natural log of 2, this here is 0.693. You can throw that into your calculator if you like. Let me double check myself. Yep, 0.693. Think about what these values are going to give us. So 1 is somewhat close to 0.693. If I did 1 minus 1/2, now I'm at 0.5. That's pretty close. If we then did 0.5 and then plus a 0.33, that's going to give us to 0.833. That's if we come here. And let's say we go to our 4th term and we now subtract 0.25. What that gives us is 0.583. That's if I go through this term. Actually, let's do one more so we can get a little bit closer. Add a 5th term. So now let me add 0.2 to that. And that would jump us to 0.783. What should happen if I now subtract and continue to do this, the more and more terms I add on the left, the closer and closer and closer it will approximate the value that I am looking for. That's one of the reasons we can use power series. That's one of the things that we can use them for. Okay. So a Taylor series is a power series first and foremost, and it says a power series expansion about a point x equals a that is useful again in approximating the value of a function as long as we stay around the point where we're expanding it. Similar to what we just talked about, the more terms we involve in the series, the more accurate the approximation will get. In some cases, the Taylor series and the function will converge everywhere. So the one that we did the other day, I had you change your window to -2 to 2 because the graphs only would converge between a -1 and a 1. You can reference the previous video if you'd like, but that's what we were talking about. Some Taylor series will produce an exact clone of that function everywhere from a -infinity to infinity by simply expanding it around a point, which we'll talk about what that means in a second. So it says by understanding the behavior of a function at a single point, you will sometimes be able to construct the entire function. Which you probably don't know what that means, but we're going to do that now. So, Taylor series. You'll see here, pretty messy stuff. It's not as hard as it looks, but this is a Taylor series. Here's our series. A couple things. Series, again, would imply every single term that we could come up with. So the only way you can write a series is the general term. The general term gives you every series. When we start writing it like the right-hand side, this is what we would call a polynomial. Keep that straight. Series is the general term. Polynomial is however many terms within the polynomial that I want. Let me erase these now so we have a little room to work. But that's what a Taylor series is going to look like. So if you understand here, what this is telling us is we want our functional value. So look at this guy here. This is our functional value at whatever a is, so wherever we are centered at. So whatever a is, that's also going to be what we put here, x minus a to the k power, and then divided by k factorial. So understand, if k is a 1, that means that's our first derivative. We would have x minus a to the first power, and then we would want a 1 factorial. If k is 2, that means it's our second derivative, x minus a squared divided by 2 factorial, so on and so forth. So if we look at how we're going to find this, what this really is, f of a, notice how there is no tick marks, so that's basically no derivatives, and then you would have x minus a, to the 0 power. That's why it doesn't show up here, because that would be a 1. And then we're dividing that by a 0 factorial. This is always interesting. Some people don't believe it. Oops, let me not do that in here. So let's clear all this out. You can take a second and guess what you think 0 factorial would equal while I find this. I gotta remember where it is. Around a little bit. It's underneath math, and when you go to math, go over to probability, go on down to number 4, hit enter. Everybody make their guess what 0 factorial is. Oops, I'm a little too excited. And 0 factorial is, voila, a 1. Go figure. All right, so 0 factorial is 1. You can wrap your head around that for a little while. There are little shortcut tricks that I could show you, but in the interest of being short and sweet, I'll leave that up to you. You can go to YouTube right now, close me out, minimize me, try to figure out what that is, but 0 factorial is a 1. If we continue on, understand our pattern. So this is no derivatives, no power, and no factorial, 0 factorial. This is our first derivative, first power, first factorial. Second derivative, second power, second factorial, third derivative, third power, third factorial, so on and so forth. All right, so what our guy Taylor found is that by understanding just our functional values and all of our derivative values, we can actually, sometimes the entire function, but we can certainly construct our function within the interval in which it's going to converge on. So number 1, what you are going to do first, you're going to find a Taylor series generated by the function 1 over x at x equals a. And a in this case is going to be a 2. So what we're going to need is all of these. We're going to need a functional value, a first derivative value, a second derivative value, a third derivative value, so on and so forth. Since I'm asking you for the series, what this is really asking you is for the general term. So to do that, let's start with our function of 1 over x. Well, if we're going to do it at 2, that means my functional value is 1 over a2. If I want the first derivative, think about 1 over x as x to the negative 1 for all these derivatives, and it'll make it a little easier. So the derivative of x to the negative 1 would be negative 1 x to the negative 2. If I want the second derivative, that's a 2x to the negative 3. And a third derivative would be a negative 6x to the negative 4th. Plug in, actually let's simplify real quick. Let's rewrite these with all positive exponents now, so it's a little easier to evaluate. Plug in your 2 now for all of these, so f primed of 2 would give us a 1/4. F double primed of 2 would have given us 2 over 8. When I plug in a 2 right here, that would reduce down to be a 1/4 also. F triple primed of 2 would have given us a negative 6 over 16, so that's what, negative 3/8. So what we now set up, we're just using this big messy formula up here. So let me clean that up a little bit. So you're going to take your functional value, which is this 1/2 here. That basically means that's our 0 derivative term. You don't have to write what I'm going to write next, but just so we understand our pattern, this would be x minus 2 to the 0 power over a 0 factorial. Then we would do plus. Then we want our first derivative value, so that's 1/4 x minus 2 to the first power over a 1 factorial. Second derivative value is 1/4 x minus 2 to the second power over your second factorial. We have 3, we'll go to there. 3/8 x minus 2 to the third power over our third factorial. What we ultimately want is this general term here. This should give us the function 1 over x. Right now, you would have to say 1 over x is an approximation because now we have our variable terms. Once we find the actual series, then we can change this to an x. The series is the only way you can use an equal sign is if we know every single term, and the only way we know every single term is if we have the general term here. So let's clean this up now. So 1 over x, we would get 1/2. And then this would be 1 over 4 times x minus 2. This would be, let me rewrite this a little bit just so we can see this pattern good. Actually, let me leave this also. So we get x minus 2 to the 0 power, so 1 over 1. Actually, let's keep 0 factorial here. No, let's not. Clean it up. So 1/2. This would be x minus 2 to the first power over 1 factorial. Plus, this would give us x minus 2 squared. Take 1/4. 2 factorial would just be a 2. Hold on. Let's go back to the previous term here. Hopefully you caught that. This should be a 1/4. Here we go. If we go to this next term, 1/4, 2 factorial. If we divided 1/4 by 2 factorial, that would give us 1/8. So that's an 8. Next one, we would get minus, and then you'd have x minus 3 cubed for sure. And then you're taking the 3/8, you're dividing it by 3 factorial. So understand 3 factorial is 3. Times 2 times 1, that's going to be a 6. So this is really 3 over 48, which is 1/16. So we would get a 16. And then what we want to come up with, dot, 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 is what is our general term. So if we now look at our results here, you will see that I messed something up because this should be a minus sign here. Yeah, so just up here, just forgot my sign. So the -1 would have been here. When we would have plugged in the x value of 2, we come down here. This one should have been a negative. So this sign then, erase that, should be a minus sign. So if we now were to look at that, if in class, I would probably wait 1 or 2 minutes to see if you can come up with this. We should now be able to look at this pattern and identify what our general term is. So if you wanted to try that, pause me, see if you can come up with it. But that's now what we ultimately want to be able to come up with. First thing you should notice is we're alternating positive, negative, positive, negative. So I like to identify or use that all by itself and just do a -1 to the n or an n minus a 1, n plus a 1, depending on where you're going to start the n's at. What we would then understand is all of these have an x minus 2, x minus 2, x minus a 2. Where I'm getting the 3 from. This would have had an x minus a 2, but it would have been a 0 power. So we know we're going to have an x minus 2 as well. You have to decide where you want to start. I'm going to start mine at a 0, which allows me to keep this as a -1 to the nth to make sure I start with a positive number. That means I'm going to keep this as an n also. So I get a -1 to the 0, positive. X minus 2 to the 0 is going to be the 1 that we have in this first term over here. And then underneath, we have 2, 4, 8, 16. So on the bottom, what we would have is a 2. And initially we get 2, 4, 8. So we're increasing exponentially. This would have to be an n plus a 1. Now check if you wanted, but start plugging in 0, 1, 2, 3. It should start producing these 4 terms. That's our Taylor series. 4, 1 over x at the x value of 2. Like I would have had you do before, it says graph the polynomials formed by the first and fourth terms of your series on your calculator, and then does the series converge to 1 over x? Do the partial sums look more and more like 1 over x at now x equals 2? Since this is where we are centered, all we really did here, found our functional value, found our derivative, second, third, fourth, we can go on forever. We understand the behavior at this one and only one x value. So now what that would mean is if we go to graph this, this is 1 over x. So if I were to graph that, the reason I have my window set is so we can see what's going on at 2, since that's where we are centered at. And you can see that's what this looks like. Pay close attention to what's happening at the x value of 2. If we then go back to our graph, I want you to graph the first term, second term, third term, fourth term, so on and so forth. Let's graph the first term. Notice how at x equals 2, see they hit each other at 2. That's the only point they shared. But having only one term of our polynomial doesn't give us a great approximation. But at that one point, they're going to connect. They're going to intersect there. What I would ultimately want to do is add more terms. So if we then go back and add that second term, this is now the original function with that second term in there. With that little bit of a slope now, you'll see it starts to replicate that graph a little bit more around x equals 2. If we go through, plug in the third term, which would add this x minus 2 squared divided by 8. So if we go to our calculator, you'll see that that has now been added. If I now hit graph, it starts to actually curve a little bit so that it follows the original function even more. And notice again, all around x equals 2 because that's the values that we were calculating. So the last one that we figured out was our fourth term. So I'll graph that one. Now we're going to add this final term here that we had with the 16. So if we go to my calculator, you'll see I have that added in now. If I now hit graph around x equals 2, it starts to string itself together even more with the original function. You really can't even see the blue function as we get around 2 for a longer period of time. If we continue to do that, we can, if you want, you can do it on your own time. It's going to slowly start to replicate that graph more and more and more. That's why the more terms you include in our polynomial, the more accurate our polynomial approximation is going to be when we do these, okay? So that's kind of the big picture idea that we want to get out of this. So that's what we just did here. Do the partial sums look more and more like that graph around x equals 2? Absolutely. That should hopefully be pretty obvious, okay? So there's your first Taylor series. The next Taylor series, it says find a Taylor polynomial. So now we don't want the series. Series means we want every single term, which basically means the general term. We want a Taylor polynomial. Here's how you would be told how far we want to go. When it says of order 3, that means we want the third power, not 3 terms. We want the third power. We're going to do that for sine of x, and we're going to do that around x equals 0. What I have in parentheses here, when it says a Maclaurin series, anytime we are centered at 0, that's a Maclaurin series. So sometimes they won't even give you this information. They will just tell you to find a Maclaurin series or a Maclaurin polynomial, and then you are expected to know that a Maclaurin polynomial, Maclaurin series means we are centered at x equals 0. That's where we're going to find our functional value and all of our derivative values, okay? So same thing we did before. We're just now going to do it with a different function, and we're going to do it around the x value of 0. So what we would need is our function, which we know is sine of x. We would want our first derivative, cosine of x, second derivative, negative sine of x. Since we were going to want our third power, then we need to get to our third derivative. So then our third derivative for that function is a negative cosine of x. We're then going to evaluate all those at 0. And then we're going to write our series, or polynomial. So sine of x, this now we have to use an approximation symbol. You could also call this, so a couple ways we can write this. You could just write a generic f of x, which again has to be an approximation. And then the thing I mentioned last week is we could call this, and they sometimes will, so just be aware of this. They'll call this a polynomial of third degree. You write that as a subscript, so p of 3 of x. Then you can use your equal sign because that truly is what we're finding is our polynomial. So the polynomial approximates our function. So depending on how you write it, you want either approximations or an equal to. So let's now go ahead and plug this in. When we do these, what we want is the functional value of 0, and then we would have had x minus 0 to the 0 power all over a 0 factorial. Plus, we would then want our first derivative value, which would be 1, x minus 0 to the first power over a 1 factorial. Our second derivative value is 0, and then we'd have x minus 0 to the second power over 2 factorial. Our third derivative value is a negative 1, x minus 0 to the third power over 3 factorial. Since we wanted to power or polynomial order 3, we are stopping here because we have our third power. Clearly now this can be simplified, so let's go through and simplify this. The first term would just drop because we're multiplying by a 0. Our first real term that we would have in our polynomial is just x to the first over the 1 factorial. This term drops because we're multiplying by a 0. The next term we would get a minus x cubed over 3 factorial. That's our polynomial term for sine of x. Now, this one says graph the polynomials formed by the first through fourth terms of the series on our calculator. Let's make an educated guess. So again, you could pause me here if you wanted to try this and think about what the next 2 terms would be so that we can actually come up with a third and a fourth term. If you kind of look at this pattern here and how you would understand the next term would have given you a 0 because of the derivative, and then think about what that would be. If you wanted to try that, feel free. Pause me. I'm moving on. What we would get is a positive sign. You would get an x to the 5th over a 5 factorial minus an x to the 7th over a 7 factorial. All right. Now, in terms of our question, this is a polynomial of order 3. But if I wanted you to graph this so we can see, this should not be that. This should be sine of x. Do they converge to that sine of x curve? When we are around now, what we would want to focus on is a 0. So let me do these real quick, and then you can kind of see what this is going to look like as well. I'll know what sine of x looks like, so when I graph that, you'll know that one. And then you're going to be graphing y equals x. So now pay attention to, actually let me change my window real quick. Let's go negative 2 to 2, because we definitely want to be able to see 0. That's where we found all of this stuff. So here's sine of x, pay attention at 0, and then see at 0, this actually isn't bad. We already have a lot of overlapping between our line and the function that that line is approximating. If I went ahead and then added the next term, so minus that x to the 3rd power, oops, and then divide by 3, should look even more like the sine of x. So that's cool. If I add the next term, so plus x to the 5th divided by 5 now. That would have been our next term in that sequence. There's our sign. That should be pretty awesome. If we do it one more time, because we said the first 4 terms, so now we're going to do minus x to the 7th divided by 7, and should look even more like the sine curve. The more you add, the more you're going to be able to produce the sine of x. One of the things I don't think we really have to learn in this case, but this graph converges everywhere. So if you were really bored over your quarantine break here, if you were to start adding these forever and ever, x to the 9th over 9 factorial, or over 9. Okay, see, this is why it's nice to be in front of 30 smart people, so when I do something stupid, you guys can all yell at me before I get too far along. So hopefully you realize that I was doing this a little bit wrong a second ago, because if we go back to my graph here, what I should be dividing by isn't 3. It should have been a 3 factorial, should have been a 5 factorial, it should have been a 7 factorial. What I showed you a second ago, you can rewind it if you don't believe me, is 3, 5, and a 7. And it looks like it, but now watch what happens when I actually do a 7 factorial, 5 factorial, and a 3 factorial. I was wondering why it wasn't looking any better than I thought it would. So now I actually have what we were supposed to have. X cubed divided by 3 factorial. Come over here, we have that x to the 5th should be divided by 5 factorial, not just a 5, minus x to the 7th divided by a 7 factorial. I was actually somewhat surprised and impressed that it still looked like it, but now watch how closely this would resemble the sine graph. Oh man, now it showed it to you already. You can't even see it. So let me get rid of the sine curve altogether and tell me that this pretty much looks like the sine curve, correct? And that isn't the sine curve. I deleted that. If I now go ahead and graph the sine of x, you're going to see they almost look identical. They're right on top of each other. Okay, so the sine one is very, very important. It's a really big one because we can completely recreate the sine function by using a Taylor series or a Maclaurin series when we're centered at 0. Okay, so pretty big one to understand. You typically that is something that you want to know going into that test. Okay, and that's what that gets at. Okay, number 3. Where are we at here? Yeah, we'll go through, knock this out. So Taylor polynomial of third order, this is our function. We're going to do it now at 4. We won't go through the whole graphing process. Let's just make sure we understand our formula. So if I want order 3, I need to get to my third derivative, okay? So we need our functional value. Our function, that's easy, it's given to you. The first derivative would be a 1/2 x to the negative half. Second derivative, negative 1/4 x to the negative 3/2. Third derivative would be what? 3/8 positive x to the negative 5/2. That I should check. A lot of ugly fractions there to be right. So now let's find our functional values. So this would just be a 2. Let's clean this one up a little bit. So this is 1/2 root x. If we plug in our 4, we would get 1/4. This would be a negative 1/4, and then this is a square root of 4 cubed, so that would be 64. So our second derivative, I got too many tick marks there, so my second derivative at 4 would be a negative 1/32. And then our third derivative would be 3/8. And then the square root of 4 to the 5th, I'm going to need to check this on my calculator, is 1024. Looks scary. That is a nice perfect square of 32. So it's 32 times 8. So we get 3/256. And that unfortunately doesn't reduce. That stinks. Leave that, and then we can now go ahead and say our function. Or we can say, no, that's not right on the same line. So we can say our function is approximately, or we can say our polynomial of third degree, and then we start following the little program, little sequence formula from the previous page. We want our functional value of 2. So that's our 0 derivative, 0 power, 0 factorial. Then we want our first derivative, first power, first factorial. Then we would want our second derivative. Oops, that should be 4. Second power, second factorial. Then we would want our third derivative at x equals 4, third power, and then our third factorial. That's our polynomial term. If that's all they ask for, you can leave it. I wouldn't try to simplify these if they get really ugly, especially on that day. Save your time. They do not expect simplified answers. If you went through that little document or link that I gave you, you'll see they blatantly tell you you are somewhat discouraged from simplifying that for the sake of time and in case you were to make a mistake. Hopefully I didn't make one on that problem. Some ugly numbers there. I'm not seeing anything wrong off the top of my head, so hopefully we're good. If you wanted to use an equal sign, we could say our polynomial of third degree and then just write all of this there on that line. Okay, 4. This is an old AP question. Very, very common. Like I mentioned on our little Zoom chat, pretty decent chance that the reason you have to cover this still, even though it's the last chapter of the unit of the curriculum, is you're going to get a question on this. Every single year this is a question. I would bet even this year it's going to be a question. So number 4 says let p of x equal, so this is just a polynomial of some function. We don't necessarily know what function it is, just a generic old function that we don't know to be the existence of, or what it is. You're given then the polynomial term. It's a fourth degree Taylor polynomial because you're going to see you have a fourth term. We are centered at 4, so that's how we got all these values. And then you say, assume f has derivatives of all orders for all real numbers. So they don't give you the series, they don't give us, it's impossible to give us every term and all their derivatives, but you're assuming that that is the case. So letter A, again, pause me real quick. I would hope if you're understanding a Taylor series, Taylor polynomial, that you could find f of 4 very easily. You would know what that is very quickly. F triple prime to 4, you would hopefully be able to get. I think once I show it to you, you'll think, okay, I can definitely do that in the future. But if you wanted to see if you can do that real quick. If f of 4 you're looking for, well, if this is our Taylor polynomial up at the top here, this term here is always your functional value. So f of 4 pretty simply has to be 7. This is your first term. This is your second term. So if we are ultimately looking for our third derivative term, it's got to somehow play a role with this term here. So think about in our formula, the Taylor series formula, what we would have had is our third derivative value at 4. And then we would have had x minus 4 to the third power. And then that should have been divided by a 3 factorial. That's the basic general form for a Taylor polynomial if we're centered at 4. So think about what we would have to get if this is really equal to a negative 2 over x minus 4 cubed. Notice what's common in them. X minus 4 cubed is common, so that doesn't really play a role in our answer. So let's get rid of those. What had to happen is that when we would have done the third derivative divided by the third factorial, that had to have a value of a negative 2. So you set up that little equation knowing that f triple prime to 4, instead of 3 factorial, I'm going to write it as a 6. That ratio reduced down to be a negative 2. So the third derivative at 4 would have had to have been a negative 12. Very common question, very common. If I wanted the fourth derivative, just because again our time is limited here, so if we wanted the fourth derivative value at 4, we would have known that that would have been divided by a 4th factorial. And in this case, this is our 4th term. That had to have equaled the 6, since the 6 here is what that fraction would have reduced down to. And then solve that for f quadruple prime to 4, and then that should give you what we get there. So that's what, 24 times 6. And what's 24 times 6? 140 something. Yeah, 144. All right, so that's how you can do those. So just be aware of that. Pretty common question. All right, so letter B. It says write the second degree Taylor polynomial. So let me clean this up a little bit up here so we can use it again. Write the second degree Taylor polynomial for f prime. So think we haven't done that yet, taking the derivative of one of these, about a 4, and then use it to approximate f prime to 4.3. So that polynomial up here is the approximation for f. So now I'm going to use this notation. So f of x is approximately the 7 minus 3 x minus 4. Just recopying this problem. So write the second degree Taylor polynomial. So it's going to be a second degree polynomial, but you're going to do that for f primed. So if this is f, we did the antiderivative earlier today. What I now need is the derivative. Well, if these are equivalent, or use basically their approximation, but that's what this is equal to. If I do to one side, I've got to do to the other. So if I take the derivative of the left-hand side, I'm going to take the derivative of the right-hand side. So the 7 would go away. That derivative is a 0. The derivative of this term would just leave you with a negative 3. The derivative of this is your chain rule. You take your 2, multiply it by 5. That would give you 10. And then we would get x minus 4 to the power of 1. The derivative of the inside quantity would just be a 1. If I take the next derivative, I would get a negative 6x minus 4 squared. understand what we were looking for. We wanted a second degree Taylor polynomial for f prime. So this is f prime. We are now at our second degree. We would stop right there. We would then use that to approximate the derivative value at 4.3. And since we're centered at 4, then as long as we're relatively close to 4, this should give us a really good approximation for any value close to 4, and 4.3 would definitely be that. So 4.3, definitely use an approximation symbol. They will hack off a point very quickly with this. You then go over here, wherever you have an x, you are plugging in 4.3. All right, throw that into our calculator. And it should tell us that f of 4.3 is approximately a negative 0.54. That's our derivative. Now, if you look at letter C, they want us to find a fourth degree Taylor polynomial for g of x. So g of x is different than what we're talking about. You were told that p of x is the approximation for the function f. We want to now find g of x. What g of x requires you to do is to take f, which is what you were given in the original problem, and we now want to do the integral of that, or the antiderivative of this. So g of x is equal to the integral from 4 to x for the function that you were given to work with, f, and in this case of t dt. So we're going to start this by writing the original function that you were given to work with. So 7 minus 3, the thing you do want to be aware of. First, let's throw some integrals in front of this, or an integral in front of this. We want this to be a function of t now, no longer a function of x. So instead of x minus 4, you're going to do t minus a 4 plus a 5 times t minus a 4 squared. Clear some space here for my work. The next term would be this guy, minus a 2, x minus 4 cubed. Remember what we want. We want a fourth degree Taylor polynomial. We are doing the antiderivative. So we are going to stop right here because we hopefully understand if I do the antiderivative of something to the third power, that's going to create, this third power is going to become a power of 4. We will be at our fourth degree polynomial. So g of x, and now we're going to write our polynomial, so we're going to use our approximation symbol. Do your antiderivatives, so you would get 7t minus, and then the antiderivative of this has a power of 1, so the 3 would remain, and we would then get t minus 4 to the second power, and then we divide by 2. Plus the antiderivative of this one, drop your 5, and we would get t minus 4 cubed divided by 3 minus 2 x minus 4 to the fourth power divided by 4. And then we have to evaluate that from 4 to x because it was a definite integral. Hopefully I can fit this in here. Make it a little bigger. Try to write a little smaller. So the function g of x approximated with a polynomial. Let's plug in our upper limit. So you would get now 7x minus 3 times x minus 4. So we're going to end up back in terms of x like we're supposed to, since we want this to be g of x. So wherever you have a t, you're plugging in your upper limit. Close that, minus wherever you have an x, you are now plugging in your lower limit. So now you're going to take your 4 and plug it in everywhere. So you would get 7 times 4, so that's going to be a 28, minus, this is an 8. The nice thing about the lower limit, when you plug your 4 in, so take this 4, plug it in here, here, and here, those are all going to give you a 0. That's sort of your answer. I give them a lot of credit. They are very, very clever. And you have to do something clever here to make this look like it's supposed to look. So if it's a fourth degree Taylor polynomial, it should look like a Taylor polynomial. What I mean by that, if we go to, I'm going to do this in yellow as a highlight. See how this has the x minus a4? It's supposed to, because we are supposed to be centered at 4. This has the x minus a 4, like we're supposed to. This says we are centered at 4, like we are supposed to. The one that is a problem is this guy. Let's do it in a different color. This guy. Although gray doesn't work so good, because this would imply you're centered at 0. We're supposed to be centered at 4. So here is where they get very clever. So let me squeeze this in over here. G of x would equal, take these two terms, and let's just rearrange our order so that our polynomial term now starts with a 7x minus a 28. And then we'd still have minus all the terms that I have highlighted in yellow. So now think about what you could do here. And this is, again, them being clever. We can now pull out that 7, have an x minus a 4. Then you would take this term, right, it's seconds. Why did I come up with an 8? That's a 2. Take this term, put him third. Do that. And then last but not least, if I can squeeze it in, put this term fourth, so minus 2. Then when we can actually reduce a little bit, they wouldn't care about the reducing though. There, that is your 4th degree Taylor polynomial, centered at 4 now, like it is supposed to be. That would be our final answer. Pretty sneaky stuff. All right, then letter D. It says, can f of 3 be determined by the given information? The answer to this is no. Up here, if I wanted f of 4, I could. Because this is a Taylor polynomial, we could find f of 4, because we know that would have had to have been our first term. This isn't asking you if you could approximate f of 3. We could, because 3 is relatively close to 4. But in terms of can we definitively find f of 3 from our given information, the answer is no. All we can find is any value of the functional value at 4 or any derivative of that function at 4. So we would say no, and then it is just because we are centered at x equals 4. So we could approximate f of 3. We couldn't actually determine the exact value of 3, however. All right. So good stuff here. This is stuff that I usually get fairly excited about. It is some things that people have a harder time with. A lot of creative problems here. I would bet a lot of money of your 2 questions, you are going to get a free response question on this. That is probably what I'm going to spend a little bit of time on Thursday. So you can see a few of them, how creative they are. Here is a question we just did, absolutely 100% an exact question from a number of years ago, and you will get one of these almost for certain. Okay. If you want some extra problems to look at, I would strongly recommend that to make sure we have a good grasp on this. Because for you guys this year, if this is one of your questions, it's almost 50% of your grade is just knowing the Taylor series and then everything that we have done up until this point in this chapter. So if there are any questions, reach out, let me know. If I've messed up, I know a few people have reached out about a mistake or 2 that I've made on all those reviews that I've given you. Please let me know. You are up to review number 5 right now on Skyward. If you were to look, I'll definitely post 6 and probably 7 this week. And that's pretty much all I got. Have a good day, and we will see you on Thursday.